Hello guys, and welcome back to my channel. You might have noticed that I've been away for a while, and that is because I've started studying mechanical engineering at the Danish Technical University. It's been really exciting, and I've gotten to use some really expensive CNC machines, both lathes and vertical machining centers. That's mainly why I've been away. It takes up a lot of time studying. I almost didn't even have time for work, so there definitely wasn't any time for videos. Sorry about that, but it's holiday season now, so I thought I'd teach you how to do shape optimization in Fusion 360. So shape optimization is a design tool that can be used to determine the critical loads in a body corresponding to the external applied loads. So that means if I apply a load between these two pillars of the gantry in the middle, then our shape optimization tool will tell us what our body needs to look like if we want to remove as much weight as possible while still having the critical mass of the body remaining. Let's jump into Fusion and I'll show you how it's done. Okay, we are now inside Fusion, and just to clear up any confusion, the gantry is this part of the CNC machine, and it will be moving back and forth, and it is the part where the x-axis and c-axis will be mounted to. Okay, I have already modeled our basic block of material because I thought it'd be boring to see me model this simple shape. I have divided the front surface into smaller sections here where the rails, where the linear rails will be located, and I've done this using a sketch, and then from this sketch you can press S and type in split, and then you will have to use the split face function, and it simply asks you to choose the face that you'd like to split, and then afterwards select the lines that will be used to divide the face up. We will use this for a simulation. We will apply little loads to these two faces specifically. Here you can see the dimensions of the gantry if you'd like to copy this block of material out. I have not shown the depth here, but the depth is 150 millimeters. So you can do shape optimization in a few different ways. You can have a material that you'd like to make lighter, a piece of sheet metal for example, and then you can use that. Or if you don't even know what the shape is going to look like, you can just overdo it and make a lot more material available than will be necessary. That is what I have done here. So this piece of our gantry is way bigger than the final version will be. So so in the first round of shape optimization, Fusion will tell us where the critical loads will be, and then from that we will work out how the gantry needs to, what it needs to look like. For this shape optimization, I have applied a composite material with a stiffness of 60 gigapascal. If you'd like to apply your own material, perhaps epoxy granite, you can go to Manage Materials, and you might not have that option up here. You can just type in Manage Materials, yeah. And then what you need to do is to find some random material and apply it to your favorites. That is because while the material is inside the Fusion 360 library, it is locked and you cannot change the properties of that material. So you could just choose mild steel, and you'd add this to your favorites, and you'd go up to your favorites, double click on that, and you can rename it. Actually you need to right click here to rename it. You can change the appearance, and what we will be interested in is the mechanical properties, and you can change the stiffness right here and Poisson's ratio. I looked up a quick number for Poisson's ratio, and that will be 25.25 for epoxy granite. For my composite, I have entered the following: a stiffness of 60, and we'll actually just change this to 25 and we will be good. Let's go ahead and press apply. Now when you have created your material, it is important to apply it. Just because it made it doesn't mean it's applied. So you would go to physical material, just like the appearance tab, but instead of appearances it would be materials, and you'd find your material under the favorites tab right here, and you can just drag and drop it onto the side body. Now I need to tell you that the material will actually not influence the critical loads inside the body. They don't depend on the stiffness of the material. It doesn't matter how stiff the material is, it will still have critical loads in the same places for a given body. However, if we are going to do static stress tests afterwards to verify our results from the shape optimization, then the stiffness comes into account, and that is why we have just made a material and applied it, because we don't want to forget to do that later. So now we are all set and ready to create our shape optimization. So we'll enter the simulation workspace, and I'll just delete previous simulations. Now I've set my simulation workspace up to create a static stress analysis by default. So what you want to do is when you enter the simulation workspace, you will be presented with this screen, and you'll just press shape optimization and create study. When we are in the simulation workspace, your workflow would generally be to work from the left and then towards the right, where we have our results and inspect options at last. So first, you could simplify your model. I'll not be going over this. Second, we can choose our materials. We have already applied our material, and you can see it come up here, composite X60, and 60 would be the stiffness for my material. That is just what I've chosen to call it. Next up, we have our constraints, and I'll constrain our gantry in the bottom. That means that it will assume that these faces are fixed in space and cannot move. Now, if you want to be doing a more accurate simulation, you'd have to match this this face up with the mating face of the carriage for the linear rail. So you'd actually have to draw up this surface right here, these three surfaces, which would be mated with the bottom of the gantry. We're just assuming that we have a full constraint here, just for simplicity's sake. Okay, so let's create our loads. Our loads will be applied to these two faces that we made using the split feature. This is where our linear rails will be mounted to. Now I don't want to optimize this shape where the load is going directly into the gantry like this. I actually want to be using remote force, and then I'll have the force coming 40 centimeters up above the origin, 40 centimeters from the bottom of the gantry. And that is because this is one of the areas where the machine has the most deflection. You can see it's kind of a lever. If it's mounted to these two faces, then the further down we get from kind of the bridge between these two pillars, the more it will deflect. So I want to optimize it for its weakest point. Now this gantry, I'd very much like it to have a stiffness of 60 Newton per micron. That means that it will deflect 1 micron when you apply a load of 60 newtons. Now it gets a little hard to read the decimals in Fusion when they are so small. So instead of applying a load that's 60, I'll apply a load that's 10 times bigger, so that it will deflect 10 times more. This will be easier to read. I'm gonna go ahead and press OK, and it creates a set of points and our load, and now we are almost ready to start the simulation. we actually have some options and criteria under the shape optimization tab here. We'll go ahead and press those, and we can read our target mass right here. That means that it will try to optimize a shape that weighs only 30% of the original value. You actually have a few parameters here, but you cannot change them and you cannot delete them. It's set up to maximize the stiffness, so you can just leave it as is. Now when you have created the simulation, you can actually change this value. You'd get a slider where you can see what it would look like on the different percentage of the weight, so you don't actually have to set this. Now my target mass for this gantry is about 20 kilos, between 20 and 25. So we can actually calculate how much weight we need to remove. If we go to properties, we can see that the gantry currently weighs 43 kilos, and you need to remember that this value will of course be based on the material you have applied. So yours might look different if you use a different material. So if we have a mass of 42, we can calculate what our goal would be. Our goal is 20, so that's 20 divided by 42. That leaves us with 47%. Let's check. So 42 times 0.47%. That would leave us with roughly 20 kilos. So we can go back and update our target mass to 47%. And now we are actually ready to simulate, so you can just press solve, and you actually need to solve this on the cloud. You can't do it locally, unfortunately. You can also just press on the results tab, and it will ask you to solve, because it doesn't have any results right now. Now that our results are ready, the first thing that I usually like to do is to make the mesh visible, because I find it hard to see the shape when the colors are so vibrant and there's no shadows to them really. So I'll apply this and I can get a bit of understanding of what we are working with. So if I'm going to increase the target mass, you can see that it gets bulkier and bulkier, and you can actually see the weight and the mass ratio down here. So our target was about 20 kilos. There we go. So while we are inside the results tab, we have an option to promote this mesh to the design workspace. So that is what we are going to do. And we will add this to the design workspace and press OK. Now if we hide the original body, you will find that we get our imported mesh, and we can more clearly see where the critical load inside of the original body will be. Now that you have this mesh, you can use it as a guide to model a new gantry, or cut away existing or cut away pieces from the original gantry to create a lighter and almost as strong gantry. So let's go ahead and do that. I'll copy this body and I'll make a component out of it so that we don't interfere with the original body. I'll call this optimized gantry. Okay, now I find it hard to see the mesh with this body, so what I'll be doing is that I'll right click on our component and I'll go to opacity control and I'll set that to 60, and then we can see the mesh better. And now it can be hard to select some faces if the mesh is on the same face. So what you can do is right click on the mesh and make it unselectable. Now we can only select our optimized gantry component. Okay, if I study the shape, I will find a few easy places to cut out at first. So I'll start selecting this face, and we will cut out this section right here. Now I find it easy to just make a square and apply fillets afterwards, so that is what we will be doing. Now I've actually already made this simulation before, and I know that we can remove this face and focus a bit more on creating some material right here. So I will be deleting this face right there. Now if you continue to make cuts like this, you will end up with a result that is substantially more lightweight than the original part. Now I've already done this, and I have actually inserted the final gantry into this design. So let me go ahead and show you. And this is what the final version looked like. Perhaps you come out with a different result. I'm going to show you quickly how you can simulate this to verify the stiffness, even though I have already gone over this. You need to go into the simulation workspace and create a static stress study. Now I'll just simplify this quickly to remove unwanted bodies. I'll just hide them. Now we have our final gantry. We need to apply some constraints to it. We'll lock the bottom part of it down, and we need to make sure that we have the right material, and it does look like we do. So we can go ahead and apply our loads. Remote force, and it needs to be the same as before, 40 millimeters above the bottom, and we will apply a load of 600 newtons, and we will solve the simulation. Now that our results are in, we will look at the displacement, and we can see that our gantry has a displacement of 0.0168 millimeters. Now I'm actually not really interested in that value over here. I'm interested in the deflection over here, but I can see they are almost both equally red, so I can use this instead. If I wanted to select the area over here, I could use a probe under the inspect tab, and I'd simply select the area which I'd like to read. Now if you guys come up with a different stiffness that might even be better than this, I'd very much like to see it. Now remember that you would of course have to have somewhat the same weight. If it weighs a lot more, it will obviously be easy to create a stiffer part. So let's go ahead and see how much this gantry weigh. Properties, and we can see that this gantry has a weight of 22.3 kilos. Now I think that's really stiff for what it is, and I challenge you guys to find something better, and by all means do go ahead and press this and right click and select share public link. I will definitely be sharing a link for this gantry, and I'll make it downloadable so that you guys can improve it. All you guys need to do is to slide this timestamp back to the original body to make your own optimization. I'll actually be sharing a link from a different shape optimization, this one, the one that I did before. Now on another note guys, you might like to optimize a shape for multiple loads in different directions, and what you'd like to do there is to just make a shape optimization one load at a time, and then you will end up having a mesh for each type of load, and what you will do afterwards is just make all the meshes visible at one time, so that you get a final mesh that represents critical loads in different directions. Now for a gantry specifically, I've found that the weakest direction of them all is that if you apply a load, let me show you. The weakest direction will be if you apply a load along the z-axis of the gantry. That might be the x or y axis on a CNC machine. So you don't need to simulate, you don't need to optimize the shape for different directions, because they will always be stiffer than the direction that I've shown here. So you can save yourself that trouble at least. So that was all that I had for you guys today, and I hope you learned something.